Hello everyone, welcome back to my channel. So in today's video, we're going to do a time series classification project. More specifically, we're going to learn LSTM-FCN, that is combining the LSTM and the convolutional network, and apply this to a human activity recognition data. Let's get started. So as a motivation, this is the dataset that we're going to use. It's from UCI Machine Learning Repository. Well, actually, you can also take it from this paper. Yeah, it's just that I am downloading the data from this website. Okay, so it's a human activity recognition, as I said earlier, and there are 6 activities, so 6 labels. This one. And it's recorded from the gyrometer and the accelerometer that are embedded in a smartphone. Okay, you can check out the detail about this dataset here and the paper. I'll show you the time plot. Okay. First of all, these are the libraries that we're going to use. And then if we download the data from this website, we will get a zip file. So I extract that here in this cell. The data has been sampled, pre-processed by sampling it in a fixed width sliding window of 2.56 seconds. And the frequency is 50 Hertz. So the total data points that we have for each recording is 128 data points, because it's 2.56 times 50. Okay, and this is getting the training data. We have 7352 observations, and then this is for the test sets. And this is the visualization that I want to show you. Okay, so this is the time plot of each recording for one recording for each activity. Okay, we have 6 of them. As you might have noticed in this cell, we have 9 time series. That's because they record the triaxial body acceleration, and then triaxial the total acceleration, and then triaxial angular velocity. So in each of these 3 kinds of measurements, we have 3 axes, x, y, and z. That's why we have 9 time series in total. So the plots that I'm showing you here are, we have 9 time series in each subplot. So given this data, we want to use LSTM-FCN to classify this. Okay, and I use this because I think LSTM can capture the sequences. Look at this. Look at the activities. We have 6 activities, but if we look at it closer, we actually have 2 big groups. The first group is the activities that are more idle, like standing, laying, and sitting, whereas in the second group, we have more active activities, like walking upstairs, walking, and walking downstairs. So what I hope from taking LSTM-FCN is that the convolutional part of the network can capture the shape of the time series. Therefore, they can classify the big groups accurately. Whereas for the LSTM part, I'm expecting that they can capture the more subtle differences within the big groups. Like, for example, here, the standing and the laying group. And let's look at this light green, the green plots. the green line here, they plot the same thing. So the same color refers to the same variable. Okay, and we can see that the line, the green line in the standing label hovers around 0.1, whereas for the laying, the same line, but for label laying, they hover around a higher level. So even though they have similar shapes, but the values are different, right? That's why I hope that LSTM can capture that and therefore can differentiate standing from laying activities. And then we have, while we have around 7,000 observations for the training, we have around 3,000 for the test. Okay, so let's go to the model now. As I said earlier, it's LSTM-FCN, so it's the combination between the two components. And since we're doing a multivariate time series classification, they have the M in front of it. So actually, if we have only a univariate time series, then we can use the LSTM-FCN model. But they also have the MLSTM-FCN for multivariate time series datasets. Okay, and actually for this model, I have discussed this in this video, even though for a completely different dataset. And so you can check out that video first, or you can check out the my LSTM video if you want to refresh your memory about that. And then for the convolutional part, if you want to know more about that, you can check out the rocket video. But basically, LSTM is a recurrent network, and a convolutional network is basically a model that is based on the image classification. So if it's applied to time series, it's for capturing the shape of the time series. Now there's one component that is not mentioned in the name of the model, and that is the squeeze and excite block. Okay, so this block is, and by the way, I think I haven't really explained the intuition of this part in my last LSTM-FCN video. So I'm going to dive deeper here. So squeeze and excite block is more like a form of self-attention for the feature maps that are outputted by the convolution part of the network. Okay, so they can find out, they can learn which features that are most important and give more weights on that features. So what happened in this part is that in the squeeze part, they take the global average, the global average for each channel. And then in the excite part, it's basically a nested function. So they put the global average function into a nested function to get the scale. And this scale would be multiplied to the output of the convolutional part. Okay, so to combine the network diagram that I show you here with the squeeze and excite diagram, I think I'll just draw it here. So the model starts with the input, okay, and it goes to two different parts, the convolutional and the LSTM part. And the squeeze and the excite block happens in the convolutional part of the model. The convolutional part has 3 stages of convolution layers. Okay, so I'm going to draw the first stage only. So the first is convolutional layer of 1 dimension, followed by followed by the batch normalization plus ReLU activation. And then the output of this is called U. Okay, and this U matrix goes to the squeeze and excite block. But first, the squeeze layer, which is again the global average. So more specifically, the global average pooling layer. Okay, and the output of the squeeze is called Z. Okay, and this Z is put into the excite layer. Okay. And then the output of the excite layer is called S, or the scale, that is going to be multiplied with the U, the output of the ReLU activation. So the last step of the squeeze and excite block is multiply. Multiply. So the output of batch normalization and ReLU goes to two different places, the squeeze and the multiply layer. And that gives us the output of the first stage of the convolutional part. So this is our first stage. And for the second and the second and the third stage, they are identical as in the first stage, except that the total kernels and the kernel sizes are different. So just to clarify, this is the convolutional layer, and then followed by, and then followed by the, the ReLU layer. And then for the squeeze and excite block, it covers this part. And then for the LSTM part, it's more straightforward. First, it goes to a dimension shuffle. So it's basically permuting or like transposing the data. The output of that goes to an LSTM layer, followed by a dropout. And that's it. So the convolutional part of the model is bigger than the LSTM. After the third stage of this convolutional part, we have the final output of the convolutional model, convolutional section of the model, and then that would be concatenated with the output of the LSTM part of the model. And then after the concatenation, they put it into a dense layer, like a fully connected network. And there we have it. There we go. We have the output. Okay, so before implementing the model, I just want to show you the distribution of the labels in the train data. It's not really uniform, but it's not that severe. Okay, the imbalance is not that severe. And this is the distribution on the test data. It looks pretty much the same. Okay, so now let's look at the model. So for the model, I used the original code. So let's go to this link. So this is the original library that is that is implemented by the authors of the paper. But if we want to use this, we have to download the repository and you run this pip install the requirements. And one of the requirements is TensorFlow 1. I want to use TensorFlow 2, so that's why I don't follow this instruction and instead copying the exact model that I want to use. Besides, I want to change the parameters, like the total kernels, the size of the kernels. So in convolution, we have the kernel sizes, right? That is the window size that we want to slide through the time series. And for each stage, they are different. By default, it's 8, 5, 3. So 8 for the first stage, and then 5 for the second, and 3 for the third. But I want to use different values. Okay. And then for the total filters, I'm going to use different values as well. But here, actually, the filters describe the total kernel. So in the first stage, they will use 128 kernels, each of which have the length 8. That's by default. Okay, that's what it means. Okay, and then for the LSTM cells, they want to use 8 cells in each, in the LSTM layer. Okay, and then for the attention, in the paper, they have two models actually, LSTM-FCN and a LSTM-FCN. So if we set attention to true, that means we want to insert the attention layer before LSTM layer. In other words, if we set the attention to true, that means we kind of have the attention mechanism not only for the convolutional part, but also for the LSTM part of the model. And then another modification from the original model is, so yeah, this is the original model that I'm copying, the generate model function. As you can see here in generate model, they don't have the attention layer, right? They put it in the generate model 2, if I remember this correctly. Let's see. Generate model 2, yes. The generate model 2 function has the attention LSTM function. But here in my generate model, I put this if and the condition. But yeah, not completely the same either, because I use the use causal mask for the attention. This is just my little experiment that I don't think worth mentioning for now, because I'm not going to use attention at all. So yeah, in this video, we're going to always run this branch instead, the LSTM layer only. Yeah, so this is our model. And then, yeah, I'm going to do a little experiment here. So yeah, this is my another modification, which is no dimension shuffling in the LSTM part. I'll talk about that later. Okay, and then this is the squeeze and excite block. Okay, so for these experiments, I'm going to use the same parameters. That's why I set the configurations first into a dictionary. Like the size of the kernels would be 64 for the first stage, and then 20, and then 4. And the total filters is 64, 128, and then 64. Okay, so that means I have 64 kernels, each of which has the length of 64. And then in the second stage, I want to use 128 kernels, each of which has the length 20. And the same goes for the third stage. And then the LSTM cells, I use 40 units instead of 4. Yeah, because I want to try, maybe they can differentiate better between the idle activities or within the more active ones. And then lastly, I want to see the robustness of the model. So I'm going to train this 10 times. Let's run this. So each time we run this, they will build the model here, and then we compile the model, and then we fit it with 8 epochs, and then I'm going to predict it right away to predict it using the X test, and then lastly I'm going to save the model. As you can see, with that parameters, we have 264 case parameters. As for the metrics, I'm using 3 different metrics: the accuracy, AUC, and F1 score. While waiting for this, as you can see here in the model, even though I said that the dimension shuffle happens in the LSTM part, but in the implementation, we actually have permute the input right from the start, right from when we feed the data to the model, because the input shape is n variables and length of TS. So 9 and then 128. So this is not really, this might seem counterintuitive, I mean, with the API of the LSTM. The LSTM API is actually, you have to put in the input with the shape length of TS and then the total channels or the total variables. But here, if we put the matrix of shape 9 and then 128, that means we take the length of the time series as in the LSTM API as 9. You get what I'm saying, right? So that might seem counterintuitive. But yeah, that's why I want to try to apply this model again, but without a permutation. And then for the convolutional part, before they go into the 3 stages of convolution layers, they permute it first. So for the convolutional part, they will it will be consistent with the API of convolution in TensorFlow. Maybe we can see this. So this is the convolution layer documentation, and the input is this. So if data format channels last, which is the case, after we permute it, so you see the input is 9,128, right? After we permute it, we have 128 and then 9. 9, which is the total variables or the channels, and that is consistent with the API here, with this. So even if we call the permute layer before going into the convolutional part, but that is actually because we have permuted right from the start, right from when we collect the data here. When we stack the recordings, I stack it on the first axis. That's why the total variable is 9. That is the dimension, the second dimension, instead of the third dimension. If that is confusing to you, even right now, sometimes I still need to think which one is the total variables, or like which one goes first. Okay. So yeah, we have done the training now. Just remember that what I wanted to say is that the implementation code is still consistent with the theory. Okay, now let's look at the results here. This is my custom function for displaying the metrics. And then I will start by reporting the AUCs. So this is the average AUC, and the range is this. It's quite stable. And then, yeah, this is for the accuracy. The average accuracy is 91.2%, okay, which is very nice. And the accuracy range is 2.1%. So if, let's say, I run this whole thing again, I might get slightly different results, but it's not going to be really different. And then looking from this graph, we can see that the best model is model 4. Okay, so this is model 0, model 1, 2, 3, 4. The best model is model 4 because it has the highest accuracy. And now, using the best model, I want to build the confusion matrix. And this is what we have. We can see that the convolution part is able to differentiate the walking activities from the idle activities. Because we can see that when the true label is walking, either walking or walking upstairs or walking downstairs, none of them are predicted as either sitting, standing, or laying. You can see from the zeros here. But when the true label is sitting or standing, some of them are predicted as walking upstairs. I don't know, maybe we should change the kernel size, like maybe enlarge it a little bit. Instead of using 4 in the last stage, maybe we should use 10 or I don't know, a different number. Apart from that, we can see more errors within the subgroups. Like, I guess the biggest error is to differentiate between sitting and standing. And then there's also a few errors in differentiating the walking from walking upstairs. So maybe the LSTM cell is too much. 40 is too much, perhaps. That's why we have this error. And this one is very nice. The laying category is perfectly classified. Okay, yeah, and this is consistent with what we see in the accuracy graph. The best model is index 4. Okay, now in this section, I want to show you a little bit how we can use the saved model. So we have saved model earlier, right? By using the saved model, we can conserve what we already have. So yeah, we can load the model by using keras.models.load model function. And then we put the model name. I'm using the best model variable here because it might change right from when I run this notebook yesterday and now. So yeah, that's why I use it like this. And by the way, for saving, when we save the model, it's very recommended to use the keras .keras as our extension. We are using the TensorFlow, right? So yeah. Okay. So we saved our, we load the model and save it to the loaded model. Okay. There are many things that are saved in the loaded model, like the weights, the layers, and there are many things that we can do with this. Yeah, I'm going to show you that the loaded, the saved model or the loaded model conserve the results that we saw earlier. Okay, first of all, we use the compute metrics. The compute metrics method needs the test data and then the one hot test labels. So our original test label is actually just a factor with one column and 6 unique values. But when we compute the accuracy or like the other metrics, we need the one hop. So actually, I already defined this y-test dummies when we call the AUC. When we compute the AUC, I have defined this. So this is the y-test dummies is the true label, and then the prediction. Yeah, we have saved it earlier, so we can just call it again like this. And the accuracy is 0.92, which is consistent with the model earlier here. F1 score is the mean between the recall and the precision. And because the recall and the precision is the worst for sitting and standing, that's why the F1 score for those activities are the lowest. And the F1 score for the activity lane is perfect 1, because as we saw earlier, it's perfect. So the recall is perfect and the precision, it's totally accurate. And in this cell, I want to show you that the prediction is exactly the same. I'm using the loaded model to predict again the test data, and I'm saving it as predict again. And by using this line, calling the array equal function from numpy, we can confirm that predict again, the re-predicted from the safe model, is the same as the prediction from the one that we have earlier.